In the previous section on error sanctioning with the logistic regression model, we defined a probability distribution, and then using the maximum likelihood estimation, we found the binary cross entropy loss function. In this section, we're going to define another probability distribution, but this time around, which takes in the number of classes. So instead of just having the product of some terms, here we have the product of these terms, but which depend on the number of classes, or rather the actual class in which we are working, because here we have multi classes. So we have the product from I equals 1 to m, where m is the number of data points in our data set, and then the product from k equals 1 to the number of classes. So we go through each and every output or each and every class. Here we have yik pred, which is a function of theta and x, to the power of yik target. Now recall that this is our target, and then this is the output from our model. And here the I signifies each of the data points. So if we consider that if we take this off and we're working with a particular data point, we just have yk, and then k now is for each of the outputs. That's for one output. So if k is equals 1, we're dealing with the first output, k is equals 2, the second output, up to k equals number of classes, we're dealing with the final output, or the last class. So we have yik pred, which is gotten from our modeling section, which we just saw, and then we have yik target. Now let's see how we could take this generalization and come back in the case where we had two classes, or see how this is similar to what we had done already in the binary classification problem. So when we have number of classes equals 2, this probability distribution becomes this, which is logical because number of classes now equals 2. And then we now have two products. So we have when k equals 1. When k equals 1, we have yi1 pred. So this is it, to the power of yi target, that's yi1 target, times, because this is a product, times when k equals 2, we have yi2 pred to the power of yi2 target. So that's how we have this product of this. Now, if we note that yi1 pred plus yi2 pred gives 1, that's the sum of all the different classes, the outputs give 1, then you could see clearly that yi2 pred, because from here yi2 pred equals 1 minus yi1 pred. So yi2 pred becomes this 1 minus yi1 pred, and there we go. We have the same formula we had seen earlier in the binary classification problem. Now let's see how to calculate this categorical cross entropy loss. Again, we are going to pass through the maximum likelihood estimate. So we have negative log of the probability distribution. We have negative log of this, which is what we had seen already. And then, since the log of a product is the same as a product, or is rather the same as the sum of the log, we can leave from this to this. So we have now log of this to the power of yik target. And then we send this yik target this way using the rules of logarithm. We have yik target times log yik pred. And then finally, since we know that yik pred is actually this, because at the level of the output, we apply a softmax on the theta jk xj outputs. Now this formula may seem a bit confusing, so let's suppose we had this example. So we had seen this previously under modeling. So we have this theta 01 x0 plus theta 11 x1 plus theta 21 x2. Now note that we are working here with 3 classes, and we are at the point when k is equals the second class, because when k equals the first class, that's when we're dealing with the first class. We have this, which is not what we have up here, and from the formula, whatever you have up is simply means you are at the level of that class. So taking you back, you could see that when you are at this first, so this is our first class in this case, although it's like the zeroth class, but let's say it's the first class. So this is the first class, the second class, and the third class. So this is our first class. We have what is up, and this is it here, plus the second, plus the third. And then for the second class, what we have at the numerator, this is it in the middle, that's the second class. And then we have the first and the third. And what we have here, the numerator, this is it at the third position. So this means simply here we are working with the second class. Now, looking at this formula is the exponent e to the power of the sum of theta jk xj. Now, an easy way to understand is to see that j is like the input and then k is the output. So if we leave from the j input to the k output, then we'll have this formula. And then we go through from j equals 1 to n. That is, we go through all the inputs. That's why you have x0, the first input, x1, the second, and then x2, the third input. So if we had 4 inputs, we have had x0, x1, x2, and then x3. So that's this, which is exactly what we have here. And then divided by, so this is e to the sum, and then this is the sum of e to the sum. So we have the sum of e to the sum, because we have e to the sum plus e to the sum plus e to the sum. So this formula should not be difficult to understand. So we've just defined the categorical cross entropy loss, which is kind of like the loss function we use when working with the Softmax classification. Now let's take some examples. Suppose we have this input, and then so this is the this is the model's prediction, and then this is the target. Here we're gonna have the negative, as usual we have this negative sign, times, that's in fact we have negative into 1 log 0. So we're going now through all the classes. Note that in this case we just have one data point, so m is, in fact this summation is taken off because we're going from I equals 1 to 1, so we don't have other terms here, so this summation is taken off. So we just have to work with from k equals 1 to the number of classes. In this case we have 3 classes, so we have negative 1 log 0, which is this log this, plus 0 log 0 plus 0 log 1. Now note that these outputs are gotten after we've done the softmax. And then log of 0 can be considered as a limit as x tends towards 0 from above. So in this case we have log 0, which is going to give us negative infinity. 0 log 0, the limit as x tends towards 0 of x log x, which in this case will give you 0 log 0, is going to be 0. So this gives us 0, and then log 1 is 0, so here we have 0, and this gives negative infinity. Negative times negative infinity, we have positive infinity. So we see that this loss function actually penalizes this model for poorly predicting this output. And then let's take this other case where we have this predictions done right. In this case we have 0 log 0, which is 0, 0 log 0, which is 0, and then log 1, which is 0. So here we see that our loss function gives us an output of 0. So you could check on our calculus course to understand how to calculate limits.